Hello there, it's Mr. Smith, and we're back. And today's topic is secant and tangent lines, two terms that you might have seen before in a geometry class, but we're going to extend them to our talk about calculus. So in this video, of course, we're going to do an introduction, talk about what secant and tangent lines actually are. I've got a few examples for you, and we'll close it out with a nice summary. So we're going to adventure on over to Desmos here to see what is going on with secant and tangent lines. So what I have right here with the dotted line is what we call a secant line. And basically a secant line is a line that's going to connect 2 points on a function, called secant because it's going to cut right through the function like scissors do. All right. So this particular line is going to go from -2, 0 to the point 1, 3 right here on the line. And what happens is we can create all kinds of lines connecting 2 points on a function. So here's one, for example, when x is equal to -1.5. And what happens is as the 2 points get closer and closer together, as we can see right here, so we got the blue point and this point right here at 1, 3 is staying fixed. As we continue to get these points closer and closer together, we actually end up with what's called a tangent line, right? And the tangent line is going to be that line, right, that goes in the same direction as our function and goes through a similar point as the function. And if you can see this as we zoom in closer and closer and closer, in fact, the function and the line are almost indistinguishable. This is a property that we'll call local linearity, that on certain types of functions, which we'll call differentiable, we're going to be able to actually approximate that function with what we call a tangent line. Right, and so there's the tangent line right there in black. You can see as I zoom out a little bit, it gets farther and farther from our function, the farther we get away from the point 1, 3. All right, and as we continue to go further and further away, we get a secant line. All right, so let's do a quick little summary of that so we have that for our notes. So secant line is a line that's passing through 2 points on our curve, and the slope of that secant line should be a familiar value. It's what we call AROC, or average rate of change. Tangent line, on the other hand, is a line passing through a point on a curve with the same slope as the curve at that point. And of course, we know that the term slope is going to be our code for derivative in this class. In other words, the slope of the tangent line is IROC. All right, so AROC and IROC, they play a role again in all this. Okay. So in order to create this tangent line, we're going to need two things. We need a point on the function, and we need the slope of the function at that particular point. Well, if you're going to do point and slope, the easiest way that you have to actually create a tangent line is going to be a point slope formula. There's a reason why we keep on coming back to that, and we've come back in all of our other classes. So here's an example. Create a tangent line to the graph of f of x at x equals -3 if we know the function value at -3 is 7, or f of -3 is 7, and we know f prime of -3 is equal to 4. That's code for slope. The slope of our function at -3 is 4. Can we create a tangent line to the graph? And the answer is absolutely. What we're going to do is we're going to use f prime of -3 as the slope of the line. And then we bring out our handy point slope form. Y minus y1 equals m times x minus x1. Know that. It's just the slope formula that's been rearranged. We are saying that our slope is the derivative, that's 4, and we plug in our point, -3, 7, and we end up with the line y minus 7 equals 4 times x plus 3. Now what we can do is we can use this tangent line to estimate other values that are near -3, like I just showed you on the Desmos. So for example, f of -2.9. So we just figured out that our line can be written as y equals 7 plus 4 times x plus 3. So again, we're going to approximate or estimate f of -2.9. So we use our approximation symbol right there. And we say that f of -2.9 is approximately 7 plus 4 times -2.9 plus 3. In other words, 7 plus 4 times 0.1, which makes sense. We've increased by 1/10 of a unit. So we should see an increase in our y by 4/10 of a unit, since that's our slope. In other words, we get an estimate of 7 plus 0.4, or 7.4. All right, so from this very early part of what we're doing here with tangent lines, you don't know yet how to take a derivative, but you will know soon enough. So I'm going to lead you through this. The derivative part isn't as important as understanding what's going on with the tangent line. So suppose we have a function f of x is equal to 2x plus sine of x. All right, so that's our graph in red right here. And I'll tell you right up front that the derivative of this will be f prime equals 2 plus cosine of x. Can we write a tangent line to the graph of f of x at x is equal to pi? Well, you bet. We need a point and we need a slope, or in other words, f prime at the point x is equal to pi. So our point we get by plugging in pi into our function. We would get 2 pi plus sine of pi. Sine of pi is 0, so the point is just 2 pi. And our slope we can get by plugging pi into our derivative right here, ready-made. So our slope is 2 plus cosine of pi. Cosine of pi is -1, so we get 1 overall as our slope. And then we use our point slope form. This is going to look a little weird. That's okay. You can leave it right in this notation, by the way, on any sort of exam. Y minus 2 pi is equal to 1 times x minus pi. I just simplified it just for the sake of putting this on the graph. And so we got our green tangent line right here. Notice, by the way, that the tangent line doesn't have to bounce off the function. In this case, it goes through the function. It only matters that you go through the same point and have the same slope of the function. So you can see right here that they match up right in that region. Okay, so that's what we want to see with a tangent line. Use this tangent line to approximate f of 3. So you can see how this might be helpful because our tangent line is so much easier actually to use to figure out a value than plugging into our original function. So when I plug in 3 into my tangent line, which was x plus pi, we get f of 3 is approximately 3 plus pi, all right, or about 6.142. And in this case, we notice that if we were to plug in f of 3 and use our calculator to find this out, we had to do 6 plus sine of 3, which is about 6.141. So our tangent line approximation was much faster and still pretty accurate, which is what we want to see. All right, tricky question, looking the other way. If the line tangent to the graph of the function f at the point 6, -4 also passes through the point 8, -8, what's the value of f prime of 6? So we got a tangent line that goes through 2 points. How do we figure out f prime from a tangent line? Well, we have to go the other way. The slope of this line is going to tell us what f prime of 6 is because the slope of the line was the derivative. So if we find the slope of the line connecting these 2 points, y2 minus y1 over x2 minus x1, we plug in our 2 points and we calculate and we get our slope is equal to -2. Wait, the slope of the line is the slope of the tangent line, so that means f prime of 6 had to be -2. So working backwards in that case, connecting slope and derivative is a key part of this. All right, last part right here. Suppose we had a table which describes f of x, which is a differentiable function of x. More on that term later, but just go with it for now. And I give you some selected values of f of x in the table above. Find an equation for a secant line for f of x that goes through x equals 2.560 and 3.500. So remember just a little bit ago I told you that secant lines have slope of average rate of change. So what we need to do is find the average rate of change between these 2 points. You guys are experts at this point in finding average rate of change. We just set up our nice little difference quotient, our slope between those 2 points, and we calculate it as -0.957. For the point, we can use either one. I'm going to use 2.560, comma 0.549, and point slope form right there comes in handy, and we plug in our slope is -0.957, and our point 0.549 for y and 2.560 for x. Easy. Leave your answer in that form. We got our secant line. Find a line tangent to f of x at 3, 0.141. So that's not in the table, but I'm giving you this point. Given that f prime of 3 is approximately -1, so we give a slope, the derivative, and we give a point. Well, it's like the ones we did before. We know our point has an x equal to 3, a y equal to 0.141, and our slope is -1. That's our IROC, and there's our tangent line. It's beautiful. All right, in summary, secant lines have the slope of AROC and tangent lines have a slope of IROC, and they're related lines that help us describe a graph. As mentioned before, tangent lines created using 2 pieces of information. the value of the function at a point and the slope of the function at that same point. And the tangent line goes in the same direction as our function, which allows us to approximate values of functions at certain points. Limited accuracy, though, the further we get from our x value, the less accurate our answer is. Thanks for listening, and we'll see you on the next video.